Have you ever really stopped to think about what it means when we say a machine learns? It sounds kind of like science fiction, right? Well, today we're going to pull back the curtain and see exactly how it works. Okay, let's just dive right in. You hear this a lot, and for good reason. AI is absolutely transforming everything, just like electricity did over a century ago. It's in your phone, your car, it's reshaping whole industries. We're in the middle of a massive technological shift. But that gets us to the real mystery, doesn't it? How does it actually happen? How does a chunk of code, which is really just a bunch of instructions, get the ability to make predictions or decisions all by itself? To wrap our heads around this, we're going to start with a really classic, straightforward example. This is pretty much the foundation for a huge amount of machine learning. So, our mission is simple. We're going to build a program that can look at the size of a house and give us a pretty good guess of its price. Now, the very first thing any learning algorithm needs is data. So we give it what's called a training set. This is just a table of real data from Portland, Oregon. On the left, you've got the size of a house, and on the right, the price it actually sold for. These are the examples the machine is going to learn from. The machine's whole job is to look at all these different data points and figure out the pattern. Essentially, we're asking it to draw a line that best fits this data, capturing that trend that, generally speaking, bigger houses cost more. So how do we translate that goal into something a computer can actually understand and work with? This is where we need to introduce a couple of key ideas. First up, we have what's called a hypothesis. It's just a fancy word for the machine's current model, or really, its best guess. For our little problem here, the hypothesis is just a straight line. The machine can tweak the slope and the position of this line to try and make it fit the data better. But how does the machine know if its line is any good? Well, that's the job of the cost function. The easiest way to think about it is as an error score. It measures the distance from its line to each of the real data points, adds up all those little errors, and spits out a single number. A high score means a bad fit, a low score means a great fit. So the goal, the entire point of this whole thing, is to get that score as low as humanly or machinely possible. And this brings us to the real engine of the learning process itself. How does the machine actually find the one line with the lowest possible error score? It uses this brilliant algorithm called gradient descent. Gradient descent works in this really simple repeating loop. So the machine makes an initial guess. It just draws a random line. Then it measures its error using that cost function. Then, and this is the key, it makes a tiny adjustment, a little nudge, to the line to try and lower that error score. And then it just repeats, over and over and over again, nudging the line each time, always trying to get a slightly better score. Okay, but this is the critical question, right? How in the world does it know whether to make the line steeper or flatter or shift it up or down? How does it know the right direction for that nudge? The best way to understand this is with an analogy. So imagine you're standing on a hill, but you're blindfolded. Your goal is to get to the absolute bottom of the valley. What would you do? You'd probably feel around with your foot to find which way is the steepest downhill, and then you'd take a small step in that direction, and then you do it again. That is exactly what this algorithm is doing. Let's actually see this in action. The machine might start with a completely random guess, like just a flat horizontal line. As you can see, this initial guess is it's a terrible fit for the data. And its error score is, no surprise, absolutely huge. It's a really bad fit, and the machine knows it because of that big number. It's like it's standing way, way up on top of that hill. It's what starts the process. Step by step, nudge by nudge, it keeps adjusting the line. After a bunch of these little adjustments, it's getting much, much closer to the actual trend in the data. It's literally walking down the hill. And with each step, look at that error score. It drops dramatically. This falling number is proof that the machine is learning. Its guess is getting better and better. And finally, after maybe thousands of these tiny steps, the machine finds the line that gives it the lowest possible error score. It can't take another step downhill in any direction. It has found the bottom of the valley. It has successfully learned the relationship between a house's size and its price. So what we've just walked through is the absolute core of a huge area of AI. Let's zoom out for a second and see where this idea fits into the broader world of machine learning. Our house price example? That's a perfect case of supervised learning. We supervised it by giving it labeled data, an answer key that had both the sizes and the correct prices. Then you have unsupervised learning. This is where you just give the machine a ton of data with no labels, and you just ask it to find interesting patterns on its own, like grouping similar news articles together automatically. And finally, there's reinforcement learning, which is all about learning from trial and error. It's kind of like training a dog. You give it a reward for good actions and discourage bad ones. This is the super powerful technique used to teach things like a helicopter how to fly all by itself. So think about this. We started with a super simple problem, finding a straight line in some data. But the same fundamental process, making a guess, measuring how wrong it is, and then slowly, repeatedly making it less wrong, that is how machines learn to solve problems that are just astronomically more complex. It's how they learn to see the patterns that tell them there's a cat in a photo, or to understand the structure of a human sentence. The goal changes, sure, but that core idea of learning by chipping away at error, that stays the same. So the real question is, what other patterns, hidden out there in the world's data, are we going to teach machines to see next?